So we were discussing internal diffusion in the catalyst. So welcome again to CH5010, chemical reactor theory. Okay, so now why we are doing this and why different geometries and so on is because the catalysts are usually very highly porous, and they come in various size and shapes. So there would be small pellets. Pellets would be as small as 100 microns, zero point 0.1 millimeter. Okay, that would be almost half of the radius of your hair, or 1/4 of the diameter of your hair. Okay, that's the size of particles that we are talking about. They come in small spheres, which would be 1 2 mm, that range. Medium sized spheres, which would be say 5 centimeters or 50 mm in length, and those would be in large scale reactors. Okay. Cylindrical shape, hockey puck. I talked about hockey puck and said that hockey puck, depending on how the diffusion is taking place, it might be treated either as a cylinder or as a slab. Okay, and again, if it's really thin hockey puck, it would be treated as a slab because larger surface area would be this surface area. Okay, if it is really this size, it can be treated as a slab. If it is very tall, it will be treated as a cylinder. Okay, and if it is in between, you will have to do a more complex analysis, which is not done in this course. Okay, it might be hollow cylinders. That means basically, cylinder would be like this, and it would be hollow. It could be wash coated. It could be foams. Various sizes, and all of these, the analysis have been done. We are only going to look at a few specific cases. Extension to other cases is usually the matter of figuring out which expressions are applicable from the literature. Okay. Okay, we talked about diffusion in the pores. The diffusion could be molecular or Knudsen diffusion. And those are the ones that we have considered. Anything lower than that is something that's too small of a dimension to be considered for this course. Okay, molecular diffusion is your Fick's law type of diffusion, or Stephen Maxwell's law type of diffusion. Knudsen diffusion, we have gone over the expression for Knudsen diffusion, and Knudsen diffusion is as the pore gets smaller and smaller, diffusivity reduces. As the molecule gets larger and larger, diffusivity gets reduced, and higher temperature, diffusivity is higher. Okay, that you can again see. D is directly proportional to diameter of the pore. Larger pore means it's easier to diffuse. Larger molecule means it's more difficult to diffuse. Higher temperature means it's faster diffusion. Okay, and we talked about dA net is inverse of dA net is inverse of dA molecular plus dA Knudsen. Okay, and then we also said that because of porosity and tortuosity of the pores in the pellet, you have your effective diffusivity, and this is, if not given, if not explicitly specified what is the diffusivity to use, this is the diffusivity that you need to use. Okay, oftentimes in problems that we solve in course like this, you'd either be given the effective or you'd be asked to calculate the effective. The problem statement should be fairly clear which of the two you need to do. Okay.
So,
yeah.
How to differentiate where we will use molecular diffusion and Knudsen diffusion?
How do you differentiate where do you use molecular and Knudsen diffusion? Would you use both? Okay. What do we do in research? We use both. Okay. Let's say if one diffusivity is very small, that's the diffusivity that becomes governing. Okay, that's because of the nature of this equation. So we'll calculate in research, in projects, we will calculate both DAM and DAK, okay, and use the net diffusivity. Based on our experience, we know that Knudsen diffusivity only matters in certain pore sizes and lesser. So when it comes to macroporous material, we don't even bother computing Knudsen diffusivity because it doesn't matter. Okay, that's a very good question. The question that I answered was, when do you know which diffusivity to take, molecular or Knudsen. So basically we take both diffusivities, calculate the effective diffusivity for our research. Most of the time we don't need to do that because of decades, a couple of decades of experience in the lab. So we know for a lot of materials it's just going to be the molecular diffusivity. So we either work in very, very small porous materials where it's the configurational diffusivity that matters, or very highly porous materials where it's molecular diffusivity that matters. So in our research we usually don't fall into the Knudsen regime. We usually fall into, we have materials that are really, really microporous, or we have materials that are very, very large size pores. We don't. So usually we either go with molecular diffusion or we go with the configuration aspect. So that's again, a lot of it in research is based on our experience. When it comes to this course, the problem statement would be fairly clear what you need to use. Okay, and the diffusion and reaction within the porous catalyst, irrespective of the geometry. This is the equation. Only two assumptions have gone into this equation. Assumption number one that has gone into the equation is steady state. Assumption number two is there's no convection. Okay. If you recall, only those two terms have been removed. There's actually a third assumption also, because the overall equation is like this, right? So diffusivity does not change with location. So that's also an assumption, but that's usually reasonably true. You're unlikely to get either DAM or DAK change with the location within the pore. Okay, but yeah, if it is, then you have del D del Ca. That's the expression to use. But for most part, even in research, we have not had to use del dot del. Okay. Now, we also talked about a dimensionless number called Thiele modulus. Okay, the other dimensionless numbers that we have discussed so far have been Reynolds number, Schmidt number, and mostly the Sherwood number. Okay, Sherwood number is a ratio of okay, technically it's a ratio of convective by conductive terms. Okay, what I mean by that is this term is equivalent to kg CAB minus CAL, which is essentially a convective term. This guy is at the pellet. Okay, so it's technically it's a ratio of these terms. Okay, for simplicity we will just call it as the external diffusion coefficient that you can use to what really happens at if you were to solve the overall equation. So it's really a ratio of that. Thiele modulus is a ratio of, so L square K is, or rather, sorry, K is reaction, okay, so it's a ratio of reaction divided by diffusion term. So how fast is reaction divided by how fast is diffusion. Okay, and it is square root of that. Okay, it's personally I think it's unfortunate that the word modulus was used again more than 120 years back. Okay, it's a better term to use would have been Thiele number, because what is phi? Phi is nothing but the ratio of reaction term to the diffusion term. Okay, so a better way to represent it would have been number, but again we have to go with the history, so therefore we will go with Thiele modulus. Okay, so just understand that Thiele modulus, just like Sherwood number, Schmidt number, and Reynolds number, is ratio of reaction to diffusion terms. So rate of reaction to the rate of internal diffusion. Okay, in a way, it's good that it is called a modulus because it's not just the ratio, but it's a ratio of square root. It's a square root of the ratio. Okay, so it's not a by b, it's square root of a by b. So Thiele modulus as such in that context may not be such a wrong term to use. Okay, so that's what this is about. Okay, Thiele modulus is the ratio of reaction term to diffusion term. Okay, so Thiele modulus is essentially okay. Now, because of this, what happens is this will be the expression, this will be how your effectiveness factor, I have not yet defined effectiveness factor, but effectiveness factor is an important term, versus phi will look like. Okay, this is how it's going to look like for a slab, this is how it will look like for a cylinder, and this is how it would look like for a sphere. Okay, so they follow the same pattern, but the actual values differ if we are using the Thiele modulus based on the derivation. Okay, in 1970s, what was done is we defined a generalized Thiele modulus. Okay, the regular Thiele modulus I am using small case phi. Generalized Thiele modulus I am using capital phi. Okay, generalized Thiele modulus is defined like this for an nth order reaction. Okay, let me go over what it means for a first order reaction. For a first order reaction, phi is going to be volume of the particle divided by area of the particle, square root of 2 by 2, okay, k CAS to the power 1 minus 1, which is KCAS to the power 0, which means this also goes away, DAEFF. Okay, what is volume by area for a slab? For a slab, volume by area is L. Okay, L multiplied by the surface area is volume, so volume by area is L. L is the thickness of the slab. Okay, for cylinder, what is it? It is pi r square L divided by 2 pi r L. Okay, so for cylinder, it is r by 2, and for sphere, it is r by 3. Okay, so if we use L for a slab, r by 2 for a cylinder, and r by 3 for a sphere, okay, this particular curve will move over here with the new definition, and this particular curve will also move over here. Okay, what I mean by that is if we were to plot, okay, n versus phi, capital phi, or eta, sorry, versus capital phi for all of the sizes of all of the types of pellets, this is how it will fall. Okay, two things to note, and again once we do the derivation we'll come to that in the tomorrow's lecture. Okay, two things to note is, one is asymptote at low Thiele modulus, and other is asymptote at high Thiele modulus. Okay, where phi, let's talk about slab or anything else. See, what does small value of capital phi means? If capital phi is small, what does it mean? Does it mean diffusivity is very large, or does it mean diffusivity is very small?
Very large.
Very large. Okay? If capital phi is small, that means D is very large. What does D becoming very large mean? Physically, what do you mean when it comes to reaction and diffusion? What is rate limiting? If D is very large and K is very small, what is rate limiting? K is rate limiting, right? Diffusion, that means diffusion is very, very fast. Okay, which means if diffusivity is very large, if D by L squared is 10 times larger than K, okay, 10 times larger, 20 times larger, 50 times larger than K, D by L square is say 10 times larger or 20 times larger than K, then it means that the entire catalyst pellet will act as if diffusion resistance is absent. Okay, entire catalyst pellet will act as if it is completely taking part in reaction. Okay, diffusion is extremely fast. Case number 2, that is the low phi asymptote. Low phi asymptote means diffusion is very fast compared to reaction. Okay, it is not an absolute statement, it is D in comparison with K. Okay, that can be because D is very large, it can be because K is very small, or it can be because L is small. Okay, so if the pellet is this small, okay, so think about you swimming in a swimming pool. Okay, you are the same person, you can swim equally fast. Let's say a swimming pool is 5 meters, just this distance from here to the camera, right, versus it's a Olympic size swimming pool 50 meters, okay, versus let's say you are swimming between a 1 kilometer stretch. Okay, which is more difficult for you to swim, 5 meters or 1 kilometer? 1 kilometer. Think about, you are diffusing in that swimming pool. It's easier, quote unquote, easier for you to diffuse if the swimming pool was smaller. It's easier to diffuse if the catalyst pellet is smaller. Okay, so if you take a large catalyst pellet, let's say a 5 centimeter large catalyst pellet, and break it down, so we literally we take mortar and pestle and we break it, crush it. Okay, that's literally how we do it, not very different from what we could do in kitchen with our spices. Okay, why do you break down the spices? So that diffusion is faster, the oils come out of those spices faster. Okay, same concepts. There we have applied the concept of mass transfer. Okay, you would have seen, for example, in drying and all that, if you want to get really well dried material, you will actually use smaller powders. Okay, say the instant coffee that you use. Okay, instant coffee is free dried. You would have seen the instant coffee, right? It's either very, very fine powder, okay, or it's a very porous granules. Exact same concept. Mass transfer only is relevant over there. Okay, here it is mass transfer plus reaction. But if you have larger sized particle, you want it to be very porous, so diffusivity is higher. Okay, if it is a smaller size particle, it doesn't matter, it can be not very, very diffusive. Okay, so to make your phi larger, to make your phi smaller, you either need to have smaller L or larger D. Okay. Conversely, if you are in high phi regime, you might end up going in the high phi regime because rate of reaction is very large. Okay, let us say the same pellet is there, same size pellet, same material is diffusing. Let us say we are using a very slow catalyst, let us say we are using a nickel based catalyst over here, let us say we are using a rhodium based catalyst, which is a more efficient catalyst but much more expensive. Okay, what will happen?
Diffusion is same in this, but reaction is slower in this pellet, but reaction is much faster in this pellet. Because reaction is much faster, this will see diffusional resistances. Okay. So, only a part of the pellet is very efficient, center of the pellet is not very efficient in doing the catalysis. As a result, your eta is lower. Okay. That brings me to the next question, what is eta? Okay, there is a reason why I am writing it down, to slow things down a bit, so that it registers for you. Okay. Remember external diffusion? In external diffusion, what we got? R observed is equal to divided by CAB, right? We did that. In exam you had second order reaction example. If it was first order reaction, this is what we would get. Okay. R, I will just call it ideal, just because I do not want to call it without diffusional resistance. K dash CAB. Okay. For external, is the ratio of the two, which is nothing but Kg divided by Kg plus K dash. Okay. If Kg is very large, what does that mean? Diffusion is very fast compared to reaction. If diffusion is very fast compared to reaction, eta ext is approximately 1. If diffusion is very fast compared to reaction, your phi is low and eta is approximately 1. Conversely, if Kg is much lesser than K dash, Kg by K dash. Okay. Kg by K dash, if you think about it, it is somewhat related to this. D by L was Sherwood number, right? K was the rate constant. So, you can think of K multiplied by L as some kind of K dash, D divided by L as some kind of Kg, okay? And therefore, you get a slope which is -1. Okay? They are equivalent. Okay? So, for internal diffusion, okay, and your eta is given as tan phi divided by phi. This is the eta that we will use. Tan h phi, sorry, yeah, not tan. Okay. So let us go to the tutorial. bit.ly/ch5010. Problem 5b. Okay. First, let us go over the second sheet. All of these equations, please note there is a possibility that I might have made an error while noting this down. Okay, do not rely even on my memory. Okay, these expressions are correct. Okay, Thiele modulus is defined like this, generalized Thiele modulus is defined like this. For nth order reaction, generalized Thiele modulus is defined like this. Okay, Thiele modulus small phi, generalized Thiele modulus capital phi. Okay, for generalized Thiele modulus, sphere, cylinder and slab all fall on the same line. Okay, and we are going to use the expression your eta is equal to tan h phi divided by phi. Okay. At very small values of phi, the value of tan h is approximately equal to phi. So, phi divided by phi becomes 1, that is why you get the flat asymptote over here. Tan h phi is approximately equal to 1 for very large values of phi, and that is why you get 1 by phi when it comes to very large values of phi. Okay. So, these are the expressions that we are going to use in this particular numerical problem. Okay. Oh, the tau should be 2, not 0.5. Okay, tau is written incorrectly over here, tau should be 2. I will make that change. Okay. So, the tutorial problem is okay. So, this is the problem. First order reaction K is 1.5 second inverse, diffusivity is this. What is the value of phi for L equal to 1 mm? Sorry? Yeah, effective diffusivity is 10 to the power minus 5 meter square per second. Okay, he gave the answer 0.1, that is if you are doing it in centimeters per second. Okay. Given k is 1.5, L is 1, what is the value of phi? 0.386. 7. Yeah. How will you calculate? 10 to the power minus 3 square root of okay. So, square root of 150 multiplied by 10 to the power minus 3. 0.387, all of you? Yeah, what is value of eta? 0.95. Hyperbolic tangent, not if your phi square is less than 10, sorry, if your phi square is less than 0.1, you can take your eta approximately equal to 1. Okay. So, the question was, okay, what are the values of eta where, sorry, what are the values of phi for which you need to calculate your eta? Okay. Remember what we had talked about right from module 3. In module 3, when we talked about reaction A going to I going to B, remember that we said rate of reaction 2 needs to be 1 order of magnitude larger than rate of reaction 1, at least 10x larger. When it comes to dimensionless numbers, similar type of things are valid, especially when it comes to ratio of reaction and diffusion or ratio of internal to external diffusion and things like that. Okay. So, the Thiele number that I talked about, okay, if Thiele number is greater than 10, its diffusion is rate limiting. If Thiele number is less than 0.1, reaction is rate limiting. Okay. What's the square root of 0.1? Approximately 0.3233 or something like that. Okay. So, square root of 0.1 will lie somewhere over here. Square root of 10 will lie somewhere over here. Okay. In this region, you have to calculate tan h phi divided by phi. In this region, eta is approximately 1. In this region, eta is approximately 1 by capital phi. Okay. And this is what you kind of got. Tan h 0.387 divided by 0.387, where does it lie? It lies somewhere around here. Okay. 0.1, this is 0.2, 0.3, 0.4, right? Where will 0.387 lie? 0.387 will lie somewhere over here, just before that vertical line that I have drawn. Okay. So, your eta is 0.95. Is 0.95 approximately 1? Yes, as an engineer, yeah, 0.95 is approximately 1. Okay. To be on the safer side, less than 0.35, take your eta equal to 1. Greater than 3.5, take your eta equal to 1 by phi. Anything in between, you compute tan h phi divided by phi. We are talking about capital phi, generalized Thiele modulus, or both capital phi and small phi if it is a rectangular slab. Okay. Let us see this for 25 mm pellet. Okay. What is the value of phi for 25 mm pellet? 9 point. Okay. For 25 mm pellet, it is going to be 3.87 multiplied by or 0.387 multiplied by 25, right. What is the value of eta equal to? Calculate by tan h phi divided by phi. Yeah, 0 point. What is 1 by capital phi? Just to recap, and I know some of you have said please do not waste time in recapping, but I think it is a good idea to recap. What I would like you to do and submit by tomorrow's class as part of your tutorial 5A is populate this entire table. Okay. The only thing that you are going to submit is your problem 1 for your tutorial 5A. Okay. I want you to calculate your phi, your eta. Because this is a slab, your small phi is equal to capital phi. Okay. Remember, capital phi is LC square root of K by D. LC is volume divided by area. For a slab, volume divided by area happens to be equal to L. Okay. 1 week from now, you are going to calculate eta versus small phi and eta versus capital phi. That will be another tutorial. Okay. If you want to do that in the class, we'll do that in the class, or we can take a break in that week, however you want. Okay. So, this is what you are going to do. Just to recap what we have done. Okay. What was given to us was dA, epsilon and tau. From dA, epsilon and tau, we calculated dA EFF. Okay. We were given K, that is the intrinsic rate constant. We calculated okay. We did this for L equal to 1 mm, where phi tended to be less okay. These are the things that you have already calculated. Okay. Do these calculations in fair, submit it by tomorrow. Also complete the calculation for L equal to 5 mm. Okay. That is your tutorial. Okay. This is essentially when it comes to problem solving, this is essentially what we have done today. Given a diffusivity epsilon and tortuosity, calculate effective diffusivity. Given effective diffusivity and K, calculate the values of phi and value of L. From the value of phi and value of L, you calculate the effectiveness factor. Your R observed, your effectiveness factor, remember, was R observed divided by R ideal. Therefore, your R observed is nothing but eta multiplied by R ideal. Okay. All of this and the derivation, we will talk about it in tomorrow's class, in the next class.